Damn. Okay, well, I think the problem probably is that they haven't really thought about the whole coordinate systems thing. And there's a height error as well, so none of it's fitting together. Ah, man. Okay, leave it with us, we'll sort it out. Have you ever got a phone call like that? Something's not fitting on site, the designs aren't working, someone's got to site and realised that this design that we've given them doesn't actually work. I just got one of those phone calls. I'm going to have to phone a friend. I think I might get Mike and Andre onto the case.
Oh, nice shot, Jacinda. Oh, hang on. Just take this call. It's work. I better take it. Yeah. Hello, Becky. Yeah. You what? Oh dear. I think we're going to have that little chat about datums and projections. I'm just out on a site meeting at the moment. Can I, when I get back to the office, I'll put together a bit of material about why this is important. Okay? Cheers. Right, what was the score? 6-1 to you. Your serve. Now, to understand why this is important, we need to go back to basics. And what it comes down to is a simple fact, that the world is round. Now, hopefully this doesn't come as a surprise to you, unless you subscribe to the Flat Earth Society, but this is the root of our problems. Why this is a problem? Well, unfortunately, even though the world is round, we like it flat. We like to create designs on flat pieces of paper. Now, even when we move to the digital age, we still want a nice regular XYZ coordinate system. And even in this day and age of model first, we like the world to be flat. If you've ever tried creating a Lego model on a round piece of flat plate. Now, there's many different attempts over the years to mathematically take a round Earth and put it into a flat, regular XYZ systems. Now, the most common one we use is one called transverse Mercator. And what that does is strip the world into slices and make each of those slices flat. Now, rather than pull apart my son's globe, I will take a smaller demonstration on an orange. Now, this is my map of the world, round planet. And what we attempt to do with a projection is take a small strip of interest. Let's choose New Zealand and Australia. We peel that off and we end up with the slice of Earth that we're interested in. Now, this may happen on a global scale or it may happen on a small scale, but the principles are the same. Now, if you take a small piece of the Earth, this is what you end up with. And remember, we are trying to make it flat. So how do we go about that? Well, we apply some mathematics. And lo and behold, we've got a flat piece of Earth. Now, in that process, something's got to give. And depending on the projection, that depends on what has to give. And we call that distortion. And it's that distortion that we've got to pay attention to. I'm going to hand it over to my colleague, Andre, who's going to explain this principle in a bit more scientific detail than my demonstration with an orange.
Hello, Mike, and thanks for your great explanation and introduction to projections. I really like when you were talking about applying the mathematics into it and how to bring that curved surface into the plane. So I'm gonna dive a little bit deeper into that explanation, and I'll try to visually explain what's happening, especially with the universal traverse of Mercator, Note that we have so many different projections and for different applications. So some projections will preserve area, some projections will preserve distances, some other projections will preserve the shape of elements. However, I'm not gonna go too far into those different projections, and I'm gonna be focused on the universal traverse of Mercator. So let's jump in, and I'll try to visually explain what's happening. So here we got an example of the cylinder of the universal traverse of Mercator intersecting with the Earth. And then we're gonna have that slice that Mike was talking about, that he removed from the orange, and a section into it. So from now, we're gonna jump into AutoCAD. So I try to reproduce the section that we were looking at the previous video, so we can better understand how the distortions are gonna be applied for bringing that curved surface into the plane. So here's the line of the cylinder intersecting with the ellipsoid of the Earth. Then on the center over here, as you can see, we got an arc. That's the, imagine it, that's the arc that's formed with that orange, that slice of orange that Mike was talking about, and we need to project that on the plane. So this distance, if you can note, it's bigger than the distance that we're gonna have on the plane for projecting all these elements and this information on a plane, right? So on the center of the universal traverse of Mercator, we're gonna have a reduction in scale factor of 0.9996. So any distance that's gonna be measured here needs to be reduced to fit on that segment on the plane. Then we have points that go outside of that area of intersection of the cylinder. Then we have an ampliation scale factor. If you look on the arc over here, it got a shorter distance compared to what's going to be projected on the plane. So from this point of intersection, where we have a scale factor equal 1, because we don't need to reduce or make it bigger, so the scale here on these intersection points is going to be 1 or very close to 1. And as we go away from this intersection, we're going to have an ampliation scale factor, which is greater than 1. So I loaded the UTM zones on Google Earth, so you can better understand how these cylinders intersect with the Earth. So those are the limits of each zone. In total, we have 60 zones, and they are 6 degrees each zone. The cylinder is actually not intersecting on those lines, but a little bit inside of those lines. So as you get closer to the edge of the zone, you might have that ampliation scale factor. Then somewhere around here, it's where that cylinder is intersecting with the globe. So scale around this area might be very close to 1. And then you start having a reduction scale factor up to the center of the zone, which is 0.9996 for the center of that zone. And back again to scale 1, where the cylinder is intersecting. And then as you get close to the edge again, you have an ampliation scale factor. So I hope now you have a better understanding about the UTM projection. And if you're a designer, engineer, and you get some plans in MGA, for example, just keep in mind that it might not represent the real dimensions of features. So for example, if you're on the center of the zone, you can have up to 40 mil difference from what is on the planes to what the actual dimension is out on the field. And it can vary as it goes to the sides of the zone, or even past the zones of intersection, which can be bigger, the dimension that you get on the planes compared to the real dimension. So for example, a building that's 100 meters out on the field, if you get the planes and measure the points on CAD, you might find out that it could be, for example, 99.960. Okay, so I'll handle back to Mike, and he'll give us a few more examples about some specific case. It's on you, Mike.
Thanks, Andre. That's a great description of the universal transverse Mercator projection, and helps us understand why a metre in your model does not always equate to a metre on the ground. If you want an extreme example of this in action, you need only look at a common map of the world. Now, if you think back to the description of the transverse Mercator projection, the piece of paper or cylinder is wrapped around the world like this and unravelled to create your flat piece of paper. The common map of the world is actually the grandfather of the transverse Mercator projection. It's actually the original Mercator projection, where that same cylinder is wrapped around the equator before it's unravelled. Now, what you see is the effect of scale distortion at the top and the bottom of most common maps of the world. And if you look at a classic example, let's say Greenland, and compare it to a country like Brazil, where Andre's from, you'd more or less think they're the same size. Well, this is a common misconception, because Greenland and Brazil, well, Brazil is actually 4 times bigger than Greenland, but that's the extreme effect of that distortion at the peripheral of a Mercator projection. Now, this is why they limit it to zones around the globe of no more than 6 degrees. And this works pretty well as an off-the-shelf projection in many parts of the world. In fact, I've worked in parts of Africa before. They commonly use the UTM projection. And of course, Australia, where they adopt the same zone system. Now, country the size of Australia, if you tried to do one projection to cover the whole country, you would end up with massive distortions out either side, which would trip you up in most applications. However, if you're a smaller country, you've got the luxury of potentially moving away from the UTM zone projection and adopting your own. And that's exactly what happens in many parts of the world. United Kingdom, for example, they've created their own transverse Mercator projection, centered around 2 degrees longitude, not 3 degrees as the UTM projections are. And they've adopted a scale factor of 1 at the center, which means pretty much that developed cylinder is sitting just on the surface, not below it, if you think back to Andre's diagram. What that means is the distortion around the United Kingdom from that projection is minimised for the size of that country. If you go to even smaller countries like, let's say, Singapore and Hong Kong, then they've got the luxury of adopting an even more customised grid to that specific location, and therefore scale factor can be almost negligible for most applications. Now, if I relate this back to fruit and vegetable, what this means is, depending on where you are in the world, over a 200 metre baseline, your distortion could be as small as a pea or as big as a carrot. So you do have to pay attention to it. Now then you get situations like my home country, which have complicated this even more by trying to do the best of both worlds. Down here in the bottom of the planet, they have a national coordinate grid, not unlike the United Kingdom. They call it New Zealand Map Grid. And they've chosen to adopt over 20 individual projections around the country and the outer islands to try and get the benefits of our very small country projection which minimises that distortion. For those who've worked in Auckland before, you may be familiar with the local example of this. It's called Mount Eden 2000. But here's the big issue. You can't just take from one coordinate system to another with an easy translation in CAD. Because of these distortions, there's actually quite complex mathematics in the background that relate each projection back to a curved Earth and then back to a flat projection. So if you try and transform from one projection to another with a straight shift in CAD, chances are you are going to introduce scale distortions, rotation distortions, and any manner of other distortions. So my advice is, please speak to a geospatial professional before you attempt to move from one to another. And in a country like New Zealand with many coordinate systems, this happens all the time, particularly when you receive data sets from other parties and which differ from the coordinate system you've chosen for your project. Another problem we come across is the fact that from time to time, datums and projections need to be updated to keep up with technology and the times, and in some cases even plate tectonics. A recent example of this has just occurred in Australia. I'm going to hand over to my colleague, Stuart Gordon, who can explain this unique situation in a little bit more detail.
Hi folks, I'm here to introduce GDA 2020 to you. It's Australia's new datum. From time to time, jurisdictions like Australia like to refresh the national datum. For us here in Australia, it happens every 20 years or so. And we do that because we make better observations about the Earth's surface and where Australia is on our plate. And we also have better computers and better ways of computing what the datum is. And we modernize the datum because as users, the technologies that we rely on to make measurements on the Earth's surface also improve. So we demand more accuracy in our datum. So here we are at a new datum, GDA 2020, and it supersedes GDA 94. Now, it's not mandatory for any of our clients or for us to move to GDA 2020. It's a choice that our clients will make when the time is right for them, and they might not move to GDA 2020. But if they do take old data sets through, and there's no right or wrong, it's just a different way of expressing the coordinates in the data that they possess. But if they do move data from 94 or even an older datum to GDA 2020, we have robust tools to help us do that. So here's a couple of tips and tricks. First, grab yourself a GIS person or a surveyor. They're experts at understanding what GDA 2020 is and what it means. And they've got the tools to help make those transformations from older systems to the new 2020 or other systems as well. Please don't go to your CAD and make shifts or simple transformations in your CAD. There are robust tools that exist. We have them. They're freely available, so we can do those data transformations for you. In GDA 2020, there's a whole swag of things that accompany it. What you're seeing on the screen behind me is the reference system that has been launched by ICSM, the authors of GDA 2020, to help describe and work with GDA 2020. So Aurecon, we've made a tech share. We've saved a presentation on our Aurecon stream that you can refer to where we unpack GDA 2020 a little bit more. And ICSM also has some great learning modules too on their website. And I'm sure we've got some links just nearby this presentation. So check them out, grab a surveyor, and don't stress about GDA 2020. It's a great thing. It's a brand new, fresh datum that we get to work with. But we do have some cool tools that we need to rely on to help us move around those systems. That's GDA 2020.
So, now that you are aware of the issue of scale factor, what should you do about it if this caret or even pea-sized problem is too much to stomach? Well, there are two common ways to deal with it. The first, believe it or not, is to ignore it. If the scale's distortion is small enough, it's not worth lying awake about at night. And for all intents and purposes, you can assume that your model scale is exactly the same as the real world, which in many cases cannot even be constructed to that accuracy. Even if it is significant enough, let's say if you're building a tunnel, a bridge or a building, as long as the surveyor who sets out the work is aware of it, they can always adjust and deal with it during construction. Even on a larger project like a road construction site, chances are the contractor's setting it out using GPS or satellite positioning technology. Therefore, the complex mathematics in the background to translate that model to the surface of the Earth is being taken care of by their equipment. And chances are they're probably not even aware there's a scale factor in the first place. Now, the second way to deal with this problem is to remove the scale factor from the data set at the start of a project. This involves taking the scale data and scaling it back up to the one-to-one scale around a central point in the data set. Now, whilst this may seem relatively straightforward, it does open up to potential pitfalls and problems, because from that point on, every piece of data coming into the project has to go through the same rigorous treatment to ensure it's aligned, and any adjacent data may find misalignment. However, it does mean that the design and set out of that data can be done confidently at a one-to-one scale for that specific site. Now, this is more common in areas of the world where you have the larger scale factors. And if you think back to the UTM projection, for example, what this may look like, it may start looking more like a pumpkin, because through the center of each zone, the data set would need to be scaled back up to a one-to-one scale, and in the exterior extents of each zone, they'd get scaled down to get back down to that one-to-one scale. So that's horizontal projections. But we couldn't do a session like this without touching on the third dimension of the heights. And that's what we'll talk about lastly.
Now, when it comes to heights, you can stop thinking about the world like an orange and start thinking of it more like a potato. That's because there's one force that rules the universe, and it's called gravity. Now, from the ancient Egyptians to the infrastructure of today, gravity is what has been used to measure height. Now, more specifically, what we need is an equal potential gravitational surface which to reference as a height datum. Now, that's quite a mouthful, but the most common one we use is mean sea level. Now, to find mean sea level, that's the shape that the sea would create if no influence from tides or weather. Now, because of the different gravitational pulls of the Earth, different density of rock and even mountain ranges, gravity is very inconsistent. Therefore, the shape of the world, when measuring gravity, looks more like a potato.
So we have our gravity, which makes the world look more like a potato. Now, if you're an Egyptian building a pyramid, or even a builder of today, you'd simply pull out your plumb bob or spirit level to define gravity. But if you're in the business of calculating mean sea level over a much larger scale, then that becomes a bit more complex. So what they did was set up tide gauges in many different ports and measure over many different years to average out what mean sea level was. From there, they propagate out heights through benchmarks across countries and continents using precise levelling to put mean sea level definition across many areas. Now, where these levelling runs would converge, you'd quite often get potato-sized differences. And that's why in some countries where two datums converge, you'll get a slightly different definition of mean sea level. On top of that, from those benchmarks, heights would be propagated out to more marks like trigs using different technology of less accurate. So your potato-sized differences could easily be as big as a banana or even bigger. Now, more recently, technology has emerged that enables us to measure gravity as precisely as this clove of garlic. And not only that, these gravimeters are able to operate in aircraft. Therefore, we can fly them up and down country or continent level to create very accurate equal potential gravitational models. And these can be used to define height datums outside of the influences of tides or other landform and measurement techniques. Now, to use my own home country as an example again, they've done this recently, and they've called the new datum New Zealand Vertical Datum 2016. One datum to rule them all, as they say here in Middle Earth. Now, this new consistent height datum across the country, together with a new international standard of defining sea level, has created a consistent datum. But be warned, this is different than all the historical datums that were based on tide gauges. And this is the reason we quite often end up with our banana-sized problem still on projects, the size of which are not always detected until it's too late. And Rebecca, this is probably why you get so many phone calls from contractors who have slipped up on heights.
So there you have it. Hopefully now you've got an understanding of why getting the right coordinate system and scale factors actually do matter. The bigger your site, the more chance that you'll have errors if you don't pay attention to this. So make sure you come and talk to one of our geospatial experts if you're not sure what's going on, and we'll get it sorted for you at the start of your project, help you understand which is the right coordinate system to select, and help you work together with other consultants or other designers so that everything fits together nicely and there's nothing left to chance when people get to site and realise that it ain't going to work. So always happy to help, just reach out. Thanks.